Hey everybody, welcome to another episode of the Subnet Show. I am Gabriel Cardona and I'm joined as always by my co-host, the man with the most cats in all of crypto, Connor Daly. What is up, my friends?
Oh man, the cats are doing well today. One of them a little angry, but I like that tagline, especially when you bring the energy. It makes me feel proud of that. Like it might actually be a cool thing.
You're bringing the cat guy back. You're making it cool again.
Exactly.
All right. Well, today we have an incredibly special guest. We have one of the co-founders of Ava Labs and the chief protocol officer. We have Ted Yin. Thank you so much for joining us today, Ted.
Thank you, Gabriel. Thank you, Connor. Yes,
I think you misintroduced him. I think you should be referring to him as Dr. Ted Yin.
Dr. Ted Yin. Okay, yeah, you're right.
Thanks.
Ladies and gentlemen, Dr. Ted Yin just recently got his PhD from Cornell. Huge milestone. Congratulations on that one.
Thanks. Yeah, it's a long journey. It's been, 5 years. Can't imagine that.
Yeah. Okay. Well, thank you for joining us. So, as I mentioned, Ted is one of the co-founders of Ava Labs. And so, as you might imagine, so much has happened just in the 18 months or two years or so that Ava Labs has been around, and Ted has had, like one of the best seats in the world to experience so much radical change and so much innovation. So we've been wanting to have him on the show since the very beginning, especially in the context of him recently getting his PhD, because it seemed like such a huge milestone and all the success we've had. So, thanks again for having us, Ted. And we kind of follow this similar pattern with each one of our guests, where we start out with, back in the very beginning, and we try and get a sense of what their crypto journey was like. So if you don't mind, let's go back to the very beginning and kind of just tell me, what was your first, how did you first discover software, and what was the first, framework or software stack that you fell in love with?
Oh, so yeah. So, I did my undergrad in China. So, it's in Shanghai, and I majored in computer science. And usually, for college students, you don't get much chance to do very real world, like that kind of full stack engineering or very sophisticated systems. But I worked on AI, artificial intelligence, for a while as research. Undergrads usually do research in their later years, like the last 2 years. And for me, I wasn't very determined to apply for a PhD or even for a master's degree or like graduate journey. Back in 2015. I was wondering, I probably was, at lost as many of my peers or, many of you guys who were at my age. And I didn't know what I should do. And I thought, okay, doing, AI is cool, deep learning, neural network. And later on, I realized that I'm more into building, systems. And the funny thing is, usually the emphasis of doing AI related research is about having new models, like we have a new neural network, so it gives us better results. It's more math kind of flavored research. So it's about reasoning about the math and guessing why the black box, the neural network, which is still unknown, know why it works. And wonder how you can better prepare the features, better train the models. But I realized that usually I was way happier when I was setting up the experiments than running the experiments. So I felt very, it was very interesting trying to put things together, say in a speech recognition task, you want to convert like the sound wave files eventually into some words. And of course, it's a very complicated system. And there's some front end that tries to process the signals and try to prepare the signal into features and put it into something called acoustic model. So my work was mostly about that. So it actually involves a lot of system engineering. So when I graduated, I realized that, okay, it looks, I think doing system research is more interesting, at least to me, than doing AI stuff, because there had already been a lot of people trying to do AI research. I think my portfolio, my skill set may work better in the system field. And I didn't know what exactly system that I will be working on. But I think the thing that I was very proud of when I got when I finished my undergrad was, in China, it's probably different from the US. You have to put together some, undergrad thesis. Mm-hmm. So you want to work on some project and try to put something together. And what I did is I wrote from scratch a torch-like training framework. So, it involves some writing of CUDA core in C or CUDA-like language, and also try to integrate Lua language as a scripting language on top of the framework. Wow. So in the end, my tool can reproduce all the major results done by other, state-of-the-art training tool that's used by our lab. So I was very happy about it because this is, very end-to-end kind of development. I know I did neural network training system from scratch, and it worked, and it can generate a decent model that other tools can generate as well. So the other, state-of-the-art tools can generate. So very fun project. I think I also did some other cross projects, but those are less interesting if you look at them after all these years. But at that time, I was pretty interested in those projects as well. Yeah.
Got it. So you immediately on-ramped into very, very heavy, math heavy. So you said you were doing something like C. You weren't using Python, like TensorFlow or something like that?
Yeah, so the reality is at that time, back in 2016, 5 years ago, TensorFlow was there, but researchers don't use that often, at least, for special tasks like speech recognition. What I know is for computer vision people, they use, something called Cafe, or very task oriented kind of C++ program tool. TensorFlow was there. There's also like Python library called Theano, and there are many, and also Torch. And the problem is, the whole ecosystem, just like our blockchain ecosystem now, the entire ecosystem wasn't that built up. So people usually struggle with using the tools, and there seemed to be a huge gap between the task they want to achieve and the low-level tool or framework they have at their hand. But nowadays, it's more unified, and people have very standardized tools, and people use TensorFlow and PyTorch or Torch a lot. At that time, people even code up their own C++ implementation just for that research project, which actually wasted a lot of time. You can also see there's like an industrialization process, that was undergoing. Same for blockchain. Usually I use this analogy. Yeah.
So how did you transition to from AI into blockchain? And do you still follow AI? Over the weekend, I connected with Ben Goertzel. I don't know if you know who that is, but Singularity, he has SingularityNet and SingularityDAO. He was at the Wyoming Hackathon, and SingularityNet is like an AI agent marketplace, and then SingularityDAO, they're doing like baskets of ERC20s that are being traded by AI. Do you still follow AI? And then also, how did you transition from AI into blockchain?
Yeah, I still follow AI. It's very interesting to see how AI has got more mature over the years, because you can see the full industrialization cycle for the AI. For people at my age or at our age, we probably didn't see the full story for, say, cloud computing, because that happened too early, like, early 2000 or even last century. But AI is pretty recent, and now it's pretty mature. So I'm still watching that, and I also have friends, at Cornell who's now still been doing AI related research. So I still hear news from them now and then. But now AI is more, well shaped, and there's some fine tuning over it, and how to transition research results into actual products, but mostly it's on the business and product side. So it's not like blockchain, not that much interesting or excitement going on in that field. So that I think for me, the reason that I moved from AI to system and then blockchain as a system application is because I know AI is not my game. I know in order to do very fundamental work in that field, you have to be very obsessed with calculus or continuous kind of math. But I don't know why. I'm really not that type. I really like discrete math, sets, algebra, these things. I don't like doing, differential, like derivatives, like trying to do integrals. Those are not good, too continuous for me. So I figure that, although I can try to do it, it's probably, I won't be that happy. So I think, system stuff is really cool because, the reason that I got my interest in computer science or in the software, the whole industry was because when I was a little kid, and my father bought the first PC, and I was really curious about how it was built up. Although he didn't let me to use the DOS, system because he was relying heavily on that for his work. He's like an architect, drawing the sketches for buildings, and that's like his work machine or work computer, and that was a very expensive back in the 90s. So yeah, and then my curiosity grew. I guess this is why I'm more into the pure computers side instead of the math. I'm especially if you compare me against Kevin, we're like perfect fit for the Avalanche project. We'll talk about later, because he's more on the math side. I'm more on the geek or computer side. And the reason, so the funny thing is, when I first came to Cornell, before I came to Cornell, I got a few offers from different universities in the U.S. and Cornell, of course, is one of the best. And I talked to Professor Gunsier, and I just asked him, like, can I not do blockchain? I don't want to do any blockchain research. It's reasonable if you think about the time. It was in 2016. At that time, people were still unsure about where Bitcoin would go, and a lot of economists stood out and said, it's gonna die. It's gonna die soon, to this year, and they kept saying that, for the following years. But we all know what happened to Bitcoin. But at that time, you can understand that. I mean, even for ambitious, graduated students who would like to explore more for decent research or good research projects, blockchain still sounds, or cryptocurrency still sounds like more or less a scammy kind of thing. So that's basically why I told Gun, like, oh, I don't want to do blockchain. Can I do something else? They say, yes, of course, you can do, many system research. And I said, I should do distributed systems because I always found it very interesting. So then I went to Cornell, and indeed I first started by looking at consensus protocols, because don't be surprised, consensus protocols also exist in the traditional systems, and it's actually one of the basic building blocks as well. And especially Paxos, Raft, Google and Amazon, Facebook, these companies, etc. These companies use this protocol for their very low level fault tolerance guarantee. So I read a lot of papers about that from. And then in 2017, I realized that, okay, I'm doing consensus, and there's also a special type of consensus called Byzantine fault tolerance. And this is just like a different type of assumption, very similar kind of setup. So then I moved to that topic, And I thought, okay, this is really solid because it's more challenging. You have, dishonest players in the system, not like the traditional consensus, which is, benign fault tolerance, or it's called crash fault tolerance. Mm-hmm. And then one day I got a message from my friend asking about, Ted, do you know anything about, blockchain or cryptocurrency? I said, no, I have no idea what it's really about. And then he sent me over like a white paper. He told me like, are you doing research in consensus? I said, yes, I'm doing research in consensus. How is that related to blockchain? I have no idea. I think, shouldn't blockchain be about smart contracts, like UTXO, signatures? So my understanding were still naive at that time. And he said, no. So we're talking about the infrastructure. There are some project which claims to use a very novel consensus mechanism. And I was surprised, and I looked at the paper. Of course, the paper is BS, and I felt really upset about it. And I asked him, like, really? So they are trying to make a lot of money from that paper? That really should not even an academic paper. It's academic-like. But if you read it, you'll find out it's like BS everywhere. It's really even hard to write down to actually oppose the opinion conveyed in the paper, because it's just random stuff, and looks professional, of course, especially to people who are not familiar with the topic. So then I started to realize, okay, it happened to be the fact that the core research problem that I was interested in and I've been working on is also the core problem that the blockchain infrastructure struggles to solve. So this is how I got into the crypto or blockchain space. And I guess, many people have similar experience. They first, they were very skeptical about this thing. It sounds questionable. I still remember in 2016, I thought cryptocurrency is about, some cool hackers and like some Russian mafia, things like that. Good enough to make a Hollywood film, but too far away from me. Yeah.
Yeah, wow, so
that was good. That was good.
Yeah.
Go for it, Connor.
That was great. Yeah, there's several funny things about what you said. Of just the first, I was actually the total opposite of you. I hate like discrete math. I'm much more the continuous guy. I'm not very good at math. Like, not very good as in like I struggled at like my 4,000 level math courses. Like I know only like a little bit of measure theory kind of stuff. That was what I was really interested in. But like, sequences and stuff like that. But then I had this total same impression. So I guess you and I might actually be the exact same age. I don't know, but I graduated in 2016, and I had worked with Goon the 2 years prior, and we had been doing some work with Bitcoin together and some applications on top of it. And it was when I was graduating and looking for a job, I kind of like looked around and I was just like, is there anything that's going to still exist in like 6 months? And I couldn't say yes.
Right.
And so that's why I didn't actually go into the field right away. It's because I don't want to move somewhere, get ready to start my life, and then have my employment like immediately disappear when I have like no money or anything.
Right.
So that's why I joined Ava Labs when I did, after the industry got a little bit more mature.
That's right. Yeah.
So you mentioned a couple of things in there. You mentioned a BFT consensus, and then so I'm wondering, sort of in your journey there, let's talk about like a 3-phase journey: Cornell, BFT, Hot Stuff, Avalanche, consensus. Can you sort of walk me through the evolution there? Was Goon involved in Hot Stuff, or can we sort of touch on Hot Stuff? How did that all come into being?
Oh, right. Yeah. So I think many people misunderstood that, Hot Stuff was like, a project before Avalanche, first did Hot Stuff and then Avalanche, then company. No. So this is a common thing, that usually that happens in history. Usually you think, this figure or this person must have done this, and then that is like a very sequential order. But the reality is, to your surprise, to many people's surprise, Avalanche paper was out before we got started on a Hot Stuff project. So, this is,
yeah, that's absolutely a surprise for sure.
Yeah, so it's not like, because at the beginning of our startup, when we try to reach out to, investors and, supporters, people usually ask like, oh, is your Avalanche protocol based on Hot Stuff? I think that's a very serious question, because our investor, I forgot which, but one of them, like major investors, asked, like they hesitated to invest because they didn't know how each work is based on the other. And actually took Gun a while, or took our team a while to convince them, these two things are separate, and they don't have that much relation. And the thing is, so first of all, the Avalanche project wasn't even called Avalanche, or even called properly when it was first conceived. So the project on first, that was perhaps in 2017-ish, and the paper had different names. It had, I once remember the repo for the paper was named network cryptocurrency. It's really it's not a good name.
What was it?
It was called network cryptocurrency. So it's a very bold name, but it doesn't really mean anything. If you now have a project called network cryptocurrency, then it would be a little bit hilarious. But it was then called like network cryptocurrency, and when they got revised, and improved by the team in the future, it was then called Gossip Chain. So the repo is currently called Gossip Chain for the LaTeX files for that Git repo. So Gossip Chain sounds good. This is the mechanism we use. But you also would like to note that in 2017 or 2018-ish, whenever you try to found a project, like a infrastructure project, like layer one, now it's called layer one, but at that time it's just like a new chain project. Mm-hmm. You would never call your project something chain. So you won't call your A chain, B chain, because there have been so many projects called something chain. And so then later on in our paper writing, I wrote, the whole process goes on like a snowball effect. So then when Gun came to that line, he said, okay, Snowball is a good name for the protocol, and then we decided to name the whole thing as Snowball. But the problem is we had, many levels or layers of the design. So we have the simplest protocol, and we keep iterating on the original protocol to get a stronger one, and then finally the DAC-based solution that can optimize the performance. So then the question is, if you already have Snowball, how do you derive the other names for other intermediate subsystems? So then we know there's a Snowflake, there's Slush, but we need more. We need Avalanche. So then we have to shift the name by one. So the final system then was called Avalanche. So it should have been called Snowball. So that's our destination. And
when you were working on it, did you get a sense that you were working on something that was special? Like, did you feel like you were creating a new paradigm? Did you feel it?
Yeah, I felt it. So unlike other research projects, because usually, as a academic researcher, mostly the pressure for you is not because of the work itself. It's mostly because of the anxiety that someone else could publish similar thing very soon. Usually because if your idea is simple or very natural, then it's, by chance, you're not that kind of genius. Usually people don't think they're that good, and usually by statistics, if you can come up with the idea, then there must be someone else in the world that may have the same idea, who may have the same idea. So, but for this one, the difference is we were not anxious about this new idea. So we don't think, first of all, we don't think anyone else would still go. They may still come up with a similar, idea for that moment, but they will quickly give it up because it's too hard and it's too crazy. So we were pretty confident that we must be the only team or only group who had this crazy idea and who actually decided to execute it, to try to solve the problems that's on its way. And all of the problems are non-trivial. So we don't have that kind of anxiety. But our anxiety or stress was mostly from the fact that what if we just couldn't solve it in the end? Mm-hmm. So, and that there were a lot of twists in the project, and what I can share for sure now is, after all the twists, I think one day we nailed it. And the interesting part is, we had a few iterations on the core protocol design, especially Kevin and I, worked a lot together. Mm-hmm. And Kevin is like a proof checker, or the checker, or attacker. And I'm the designer, or actually we both design. It's like a good, now it's called adversarial kind of design process. You have it's called GAN or GAN in neural network. So you have a generator and an attacker. So I generate a new protocol spec. Could be very shitty. Who knows? And then based on my feeling, because the problem is protocol is like a stochastic process. Mm-hmm. So the problem for me is I cannot prove it, entirely when I design it. At least I cannot tell easily whether it's 100% correct at a first glance. So I'll pass it over to Kevin, and Kevin will try his best to attack the protocol with all his skills, and he's really good at it. So in the beginning, the turnaround time was very short. It's like, okay, one day or 1 week or several days, he would usually come back with the special case, and like, Ted, your protocol is not going to work because of this and that. So for a very long time, it was like that, because we know this direction or the idea works, but what we don't know is whether there is a solution or a simple enough solution, and whether the protocol can be proved. And we struggled for a while. And until one day, I felt, things tick together, and I sent it over to Kevin. And, Kevin was kind of tired, like, oh, your protocol is going to break, in seconds, or tomorrow I'm going to tell you it's broken because of this. And then, after that day, he didn't come back. And after a month, he didn't come back. And then I had to check on him, like, Kevin, what's going on? Like, are you looking at the protocol? And he said, yes, I looked at it. I couldn't break it easily. And now I'm thinking about how to prove it. So, that took us a while to reach that point. And so
what was it like, so most PhDs end with a research paper, and then you go get a postdoc or you get a faculty position. Most of them are not like spinning out your own startup at the same time, and then kind of building a company while you're doing your research. So I guess what was it like to have the idea, or like the experience that maybe I'm not on the academic track anymore. Maybe this idea has so much traction that we need to build something with it that's real, that's not just a paper, that's a company that's going to exist in the world, that's not just going to be an open source project on GitHub, but it's going to be a thing in a market that needs investors. What was that process like?
Okay, yeah, that's a good question. So yeah, it's very unique for me. So this is why I admitted in my dissertation that in retrospect, my journey was very surprising, but challenging and but very fruitful in the end. So yeah, it's definitely challenging because usually most of the PhD students and what you said wasn't that correct. For most of the PhDs, they don't pursue a faculty job. So that's the reality.
Sorry.
Yeah,
they go to Google, they go to Facebook.
Yeah, because pursuing a faculty career is really hard. It's like if finishing PhD is this hard, it's like I don't know. It's like have you played Dark Souls? It's a very hard game. It's like normal mode. Then faculty is the highest, insane mode where you have no sword, no shield, like naked, try to fight against the beast. It's like that. So most of the people just go to large companies, which is fine. And it's rare to do a startup. I think it doesn't. Sometimes it does not have much to do with whether this PhD is strong enough. It also has something to do with the luck. Or I actually got lucky. Goon is very practical in terms of research taste. So he's not doing purely theoretical kind of research. There are a lot of theoreticians that I worked with, or they are really good. Don't misunderstand me, but usually for if you really want to do something, or you really want to have a startup, have a working system, then it's important that your research topic or your project is very practical. It's like it's both about whether it's correct or whether it has its theory, has the algorithm, but more importantly, whether your algorithm could be implemented. It's not like do blah blah blah, and then doing that sounds like O(n) or n squared, but n is really large, or the constant is large, so your algorithm sounds good asymptotically. It's not practically good. It's really slow, and I mean, admittedly, that's been the reality, especially for cryptographers, because a lot of crypto algorithms, they're very interesting, very useful. But still, I think there are years ahead of those algorithms for them to be more practical. So I got lucky. I got an advisor whose taste is pretty in alignment with mine, and I'm also a very practical researcher. But I like to think about the theory side, or what the fundamental problem is. And as for the execution, of course, it's sometimes I did feel torn apart, between the company startup, especially was just founded, and the academic research, because these two things are not that related, because investors don't care about how many papers you publish, whereas your academic advisor or your PhD degree does care about whether you keep publishing paper, or at least keep producing research work. So and then my role at the startup was also kind of special. But I was very happy that we had a dream team, because we had Steven, and Steven joined our startup on day 1 or 0, and I think that was like in the fall of 2018ish, or in the end of the summer of 2018ish. That's the time when I just so to add to the to answer Gabriel's earlier question. So the timeline was like in the May of 2018, Team Rocket released the paper, and I think Kevin went on to do his own startup, something totally unrelated to blockchain, and I started my internship at VMware, so working on some cool research project, which was later known as Hot Stuff. And Goon was left alone at Cornell, and definitely he wasn't very happy about it. He joked about it. He joked about like, Ted, whenever you come back, my office will be gold plated. you know. I have cake covered with gold foil. I won't let you have it. So he joked about it. But we came back after I came back after my summer intern, but the hot stuff research still went on. And then, I transitioned my efforts also to the foundation of the startup. And that time, Stephen just picked the language for the for Avalanche project, which is Go language, and funny enough, it's just like a random choice. it's like Gun said, Rust or Go. We would like to use some cool language, more than new languages.
How do you feel about that in hindsight?
Yeah, so late, like I guess 1 year later, I actually talked chat with Stephen about that. So I said in retrospect that was an excellent choice because it's not about following Ethereum, because we didn't do that by following Ethereum. It's mostly about, because Ethereum at that time also had parity in the official implementation, both Go and Rust implementation. I think for the sake of community, it's good to choose Go language. We all know that it's hard to say whichever is better. It starts a war, and I personally I like Rust more than Go. If I just write a program for my own purpose, or especially for infrastructure of distributed systems. But I also see the advantage of Go because I played with it. It's a good language. It's easy to pick up. Its syntax is simple, and it's really hard to have crashes or sig faults in Go. Some people may disagree, but it's like a modern version of Java, but feature less Java. It's like a modernized version of Java, and people are really happy about it. So that's it. I mean, then people can write code. The thing that usually in software engineering, the thing that that's hard to predict is the quality of the programmers. So you get programmers all over the world. They could all submit pull requests. They can try to tweak your code here and there. And the problem is, if the language itself has very steep learning curve, then it's perhaps not a perfect fit for a community language. Like if you use Rust, then perhaps it's only about your own core team, or only 2 to 3 people trying to develop the whole thing. So because it's hard to do quality control of the code, and people can easily create a lot of bugs or issues with low-level languages, or languages that are harder to learn, or languages that take a lot of time to learn. So yeah, overall, Go is definitely a good choice. It's slower than Rust for some applications, but it's good for collaboration, and it's very, very inclusive.
Okay, got it. And so, knowing that, dom me in on my details here, because I might step all over this, but knowing that Libra was created with Hot Stuff, I guess let's start there. Can you define the relationship of Hot Stuff to Libra? Go ahead.
Before we talk about Hot Stuff a little bit, could we just define for our listeners who don't know what that is, and just kind of maybe just give a quick
sure, yeah. So usually people tend to think there are lots of consensus protocols or algorithms on the market, but in reality there aren't. So there are only to us, at least to researchers, we usually think there are two kinds of roughly, when it comes to blockchain, there are two very different kinds of protocols. One is, of course, it's called Nakamoto consensus, which corresponds to what Bitcoin or Ethereum uses. It uses proof of work, keeps mining, like a Git commit, a history of Git commit. And on that front, Git is also like a Nakamoto consensus, because a commit is also a proof of work, coding work. But the other kind is usually called quorum-based systems, or we also call it classical consensus, because it's pretty classical. It was first on, or at least the name Byzantine fault tolerance. The reason that the word was chosen was all because of Lamport. So Leslie Lamport, who got a Turing Award, I think a couple of years ago. And he's really famous in systems world, and he has done a lot of research works that are very impactful to the whole system industry. Like Paxos and TLA in many different subfields. So that research was already there, perhaps in around 70s, last century. So that's like you can count the years. So at that time, you can imagine what kind of computer they were using. So perhaps people at that time still use typewriters. They don't have printers. They submit their papers after they typewrite the paper, and they don't have powerful computers. And so and then the things got developed over time. So usually that kind of protocol is based on voting. There's no proof of work or mining process. It's more like a vote in the Senate or in the Congress. It's like we know there's a group of people. We know the senators. They cast their vote, and if you achieve a supermajority, like for some protocols, typically they need so-called 2f+1. It's like 2f+1 out of 3f+1 nodes. F is the number of voting nodes. So it's like 2/3 from the entire crowd, which is also very similar to politics. You get 2f+1, 2/3, and then you form something called quorum. So quorum is also like it's a very old word. And you don't normally use quorum in your daily life. And I didn't even know what quorum is until I looked it up in dictionary. So it just means a threshold number of people.
With no, pardon me for interrupting, with no smart contracts, how was the tallying of the voting done?
So the voting here in the protocol is not that voting, So there's actually a misconception many people had, which is many people think, okay, your protocol is based on voting. So the consensus is like, I prefer this, you prefer that. We are emotional because I like this, I want this transaction to be in. It's not like that. So the thing here is the voting, while it has the knowledge in real life, the actual system doesn't really care about the preference of the transaction or the decision to be made, as long as the decision is consistent across the network. So, either this or that, doesn't matter. So that's a little bit different from, community voting or, voting, but downing some smart contracts. So on that, in that sense, it's you can think of it not like a voting, just like messaging. I'm telling you something. I'm trying to exchange the information, and usually by the votes or by the quorum. Quorum is like a set of votes or set of messages. You can tell I know that some people know something, and you can keep doing that for rounds. Then it's like like a chain of knowledge. And finally, by the rule of intersection, you can reach an agreement. You know that because you know that good people must have already known the same thing that you have known. So that's the point that when you can make a decision. So there are two different families or different flavors of consensus, and Hot Stuff is the second kind. So it's still traditional model. And what it aims to replace is PBFT. So PBFT was born in 1999 and the end of last century. And unfortunately, nobody used that actually for their product. It's because at that time, there wasn't such, big movement for decentralization. So usually you assume the company just handles all the machines. Then there's no need to assume some of the machines could try to overthrow your entire system. They can only crash. They can be unresponsive, but they won't try to collude and try to fool your other nodes into believing something else. So that, and then also at that time, processors were very, very slow. So usually, protocol with more guarantee, like PBFT, it's more expensive. So they're way slower than its counterpart, like Paxos. So then, we all know in 2008, Satoshi Nakamoto published a paper about Bitcoin. It's like an entire system solution. And then people thought, okay, looks like it tries to address the same problem or similar problem, although it does not provide 100% safety guarantee. It doesn't say, 100% you cannot double spend. It's still immune or somewhat immune to fractional attack in the system because it's not voting-based system. It's just based on the longest chain. But it tries to address the similar problem, so they can be categorized into the same field. So we are both trying to address the same problem, which is called Byzantine fault-tolerant problem. The reason that it was called Byzantine fault-tolerant, not other, old empire fault-tolerant, is a historical reason. You can look it up. I think Lamport actually wrote about it. They first wanted to use a different name, but they found that there were descendants of that, old empire. So they just didn't want to irritate those people. They didn't want to be very offensive. So then they ended up with Byzantine, because nowadays nobody would claim they're the genuine, descendants of the Byzantine Empire. So yeah, and that's why they chose the name. So Byzantine here just means malicious or adversarial, and yeah. And then the relationship between Hot Stuff and Libra is, in 2018, when I did my internship, you may have already noticed that I did my internship at VMware. So why does it have anything to do with Facebook? I've never had my internship at Facebook. That's also like a misinformation that many people thought, oh, I did my internship at Facebook and developed protocol there. Nope. So that protocol was very pure research project. And I really like the fact, the way it is, because, it's not about VMware or research or Facebook was thinking about, oh, we're going to do a project. We're going to do a product that's worth billions of dollars. And you guys want to work on a protocol. I mean, that's also, that makes sense for an intern student. That's also impactful when you first know about it. But wouldn't it be nice that you just work on some random or, very interesting and elegant protocol that you really believe in it? So in 2018, nobody or very few people knew about this protocol. But we all think, at least, all co-authors thought this is, the protocol that's going to replace the state of the art or the best protocol of the second category. And then afterwards, it's like Facebook was thinking about its blockchain project, and it looked at different protocols on the market, and finally decided that, okay, looks like Hot Stuff is the right protocol to choose, because they have their own rationale to choose the protocol. They are like a big company, and which is both a good thing and a bad thing. The bad thing for them, we can already see they still aren't able to launch their project, although the tech is ready. That's what I heard. And the other bad thing is they have to be very conservative or very careful about the protocol or system they choose. They have to choose a very mature solution that is the best, at the time. So I totally understand, or I really think that's a good choice. So, like traditional kind of consensus doesn't have to do proof of work. It works well for a consortium blockchain, especially for that kind of blockchain. You don't have a lot of nodes, like thousands or 10,000s of nodes. And usually in that system, you have your own admission control, which is like, we have a special committee, or we have something with KYC, some, validators. So that's for their own use case. There's a lot of debate between permission and permissionless system. But when it comes to technology or comes to consensus, it doesn't matter that much. But at least, it's a good fit for their use. And the reason, and then also later on, my mentor at that time, her name was is Dalia Malki. She also jumped from VMware to Facebook in the summer of 2019. And then I got a message from her saying, you know, they plan to release or at least announce Libra very soon. And I should watch out for what I'm saying to the press or news. And definitely I wasn't part of their dev team, and I wasn't part of their, you know, decision-making team. We just, you know, worked on the research together for almost a year, and that protocol was later picked by Facebook. And I'm very happy to see that. You know, it's good, always good to have large companies getting involved in the crypto space. And for Avalanche, the core difference is many people would ask, like, oh, how do you compare, you know, these two protocols? Because usually their mindset is like one should beat the other. You know, it's like a game on the stage and have to KO the other side. But for us, for researchers, we usually work on similar stuff and we work on different stuff. And usually they don't have, you know, it's not like mine is strictly better than yours. It's mostly dependent on the assumptions, you know, but people are really tired of, you know, the word assumption. You talk about you scientists talk about assumptions or under this and that scenario, oh, it's better. But the reality, you know, in reality, it is true. It's like they are pretty counterpart for each other. So if you think about it, Hot Stuff is quorum based, so it requires very strict knowledge for the number of participants. So I have to exactly know who are doing consensus in the system. And if someone wants to join or leave, we have to do a consensus to make sure everyone knows about that. So it's very strict membership. And for Avalanche, it's kind of loose membership. And for Hot Stuff, it's like we guarantee your safety. You know, it's deterministic. It's always safe as long as you don't have more than a third of Byzantine node in the network. For Avalanche, it's like we have a tuning knob. We have, you know, trade-off between safety and liveness. It's not like you know, it's not like when you have more than 1/3, your protocol just breaks apart. And before 1/3, your protocol is rock solid. Our protocol is like, if you have less Byzantine nodes, then you may have, if you choose the parameters wisely, you have more liveness, and your system is almost rock solid. It's like Bitcoin kind of, you know, solid. But it's more solid than Bitcoin. And also for the and they actually have a common part. I think the common part is both protocol there are two common parts. One is both protocols tries to be practical, you know, and in doing that, both protocols try to separate safety from liveness in a way. So for Hot Stuff, it's pretty obvious. Like if you look at the core protocol, it's pretty simple, but it doesn't say how to make progress. So it doesn't assume when you propose a block. So no matter how you propose a block, how fast you propose a block, how many leaders simultaneously exist in your chaotic little government, it doesn't matter. It doesn't break the protocol. Whereas for liveness, you have to have something called pacemaker, and Facebook indeed designed their own pacemaker for their use. And for our protocol is kind of similar. So we can also easily detach safety from liveness to some degree, like the recent Snowman++ update. If you think about it, it's like the update itself doesn't change the safety of the protocol. It's more like, oh, we want to have a soft leader, so we have less contention in the network. But even if there's contention, even if there were two leaders simultaneously, or at least these two nodes think they are leaders, the network the safety wouldn't break. So it's like a very interesting, you know, layer on top of that. There's definitely some decoupling. So that's one aspect. The other common thing is those protocols somewhat try to learn the benefits or the advantage from both Nakamoto consensus, the first family, and the second family, the quorum-based protocols, because none of them use mining. They don't require special hardware. They both use some kind of vote based mechanism. But the difference is for Avalanche or for Snowball, it randomly samples. So you can view Snowball as like a probabilistic version of Hot Stuff. It's a very rough, kind of analogy, but you can view it like that. So in those protocols, you vote, or in our protocol we call it chits. So we collect chits or messages, and in Hot Stuff you have to ask everyone, or for the votes, the leader has to ask everyone. In our protocol, it's like you only sample a small subset from the protocol, but still it's like a set of votes. So they're also connected if you think about the common parts of these two protocols.
Wow, that was wonderful, Ted. I could listen to you talk forever, dude. You are such a wealth of knowledge. My God.
Yeah, this has been a master class on these consensus algorithms. Yeah, no, this is great.
And you know what? There's one more topic. We're already coming up on an hour, and so I want to be respectful of your time. One last topic I want to brush on, and obviously feel free to go to deep dive as much as you want, is CedrusDB. So that's another thing that's been on everybody's mind, and we wanted you to at least touch on it. Let us know what it is. Let us know what the progress of it is.
Sure. So CedrusDB is my third project at Cornell. The project I finished before I graduated, but also thanks to the company, I got the freedom and time to work on it, and hopefully that will be integrated into our system in the future. Mm-hmm. And that project is mostly about storage. So let's take a breath. No more consensus, no more Byzantine, no more adversary. Let's just talk about storage. So the motivation for the project was actually interesting or funny. That was perhaps in 2018 or even 2019. I realized when I tried to add database to my prototype for Avalanche. So we did have a C++ prototype for Avalanche to get the TPS or the numbers in the paper. And that's really pure kind of benchmark. It's still realistic, but it's not like a product. It gives like a very realistic estimation of how protocol itself behaves, by stripping off all the APIs, all the like services. And while I tried to add the database, I realized that the system cannot run or cannot maintain a relatively fast speed for a long enough time. Mm-hmm. So the reason, later on I realized one of the reason was because I had a really shitty hardware. But I didn't use SSD. I used like a HDD, like a rotational hard drive, like a magnetic hard drive. And but also on the other hand, I realized how quickly LevelDB degrades in terms of its performance when its capacity or when the number of items stored in the key value store grows. And it's not like a linear degradation. So many people envision, okay, database, it's like I have 1 gigabyte of data. It's like this, that's like performance here, and 10 gigabytes here, 100 gigabytes here. It's like a linear degradation. But that's not the case in reality. The reality is like you have a very sharp degradation initially. So if you only have like megabytes or gigabytes of data, you're fine. It's pretty fast. And then once you have, more than dozens of gigabytes, the database starts to become slower and slower. It's really slow. But when it hits the bottom, no matter how much you further add in, like, 1 terabyte, perhaps the performance will just stay at the tanking point. So it tanks pretty soon, but it maintains low performance at the bottom. So that means then you may ask, like, why wasn't it a concern for Bitcoin or Ethereum? And the answer at that time was kind of, both Gun and I said, that's because, they were slow. So the consensus was slow. And they only make, a few transactions per second. then it's not a pressure to the database, even if it's pretty much worn out. It has a lot of items. But it's definitely a problem for faster consensus protocols, especially for Avalanche or even for Hot Stuff. So then I had my interest in thinking about how to improve the storage system, because if you have all the good consensus protocols, it probably doesn't help if your overall performance is still bottlenecked by the storage subsystem. So that's why I invested my time in learning about the state-of-the-art key-value stores. And it turned out to be the fact that the first interesting thing, and also that's the thing that I mentioned to Patrick earlier today, so it's really serious stuff. So RocksDB is much better than LevelDB. And I'm surprised that still, we aren't using, I know there's a certain reason, because everyone uses LevelDB, or most of the people use LevelDB. But RocksDB perhaps is faster than LevelDB and nobody uses it. And it's pretty solid. And again, unfortunately, it's also developed by Facebook. Facebook is like, aha, look at my, we have a full universe of products for your own use. But LevelDB was designed by Google. So Facebook actually, based on LevelDB, they derived their code base. So it's like, secondary development based on LevelDB. And the problem is usually blockchains have very different workload compared to normal, when we mention normal, I mean the, cloud computing or web apps. It has very different workloads from those normal applications. And the reason behind it is because, first of all, blockchain, at least from many projects so far, although you can do snapshots, you can do fast sync, you probably still, footnotes still would like to store the entire history. That's the reality. I mean, there is a lot of proposals about trying to prune the chain, and we're also working on that. We also have our own plans, but still the reality is the chains keep growing, and which is very uncommon because, for a regular database, like your database at your school, you just record, Gabriel like aced this course, Connor failed this course, or aced the other course, and the most of the changes are in place, and your students come and go. You can just delete the student. So Connor graduated, with honor. Just remove his entry.
Trying to make up for it.
Yeah. And or the grading was incorrect for Gabriel. Correction, it's not A, it's A- or something. Who knows? So the updates are mostly in place, and the size of the database usually doesn't change that much. It definitely doesn't keep growing, right? It's like school only usually has like a constant number of people at a time, as students at a time. So for blockchain, very different. And also for blockchains, you have that weird append only kind of writing workload. You keep pushing more blocks and more entry into the database, and you rarely delete any of them. So for normal database, you may also have deletions, and that's not that rare. But for blockchain, you rarely delete anything. And so all because of these differences, I think, perhaps it's not good to use LSM based. So LevelDB is based on something called log structured merge tree algorithm. That's tailored for those applications, the traditional applications, but it may not work that well for blockchain cases. So then I worked on CedrusDB thing, and I can go on more about CedrusDB details, but we have really limited time for that. I'm also happy to talk about other stuff. If we can break 1 hour limit, it's also fine, because there are so many interesting things.
Yeah. So I just want to make sure that we give you a chance. I know you're very interested in educating in the blockchain and in the consensus space. So I just want to make sure that we give you the room to talk about anything that you want to talk about, because I know you definitely mentioned earlier you wanted to correct some common misconceptions in the space.
Yeah. So So I think I'm gonna talk about three little things, but everyone must be very familiar with these three little buzzwords or terminologies. One is TPS, and the second one is sharding. The last one is proof of work versus proof of stake. There's been a long debate going on for POS versus POW. So for TPS, what I usually put in my slides when I try to do a guest lecture or public talk is I always want to let people know, the audience know, the fact that in order to evaluate a system, especially a distributed system, which may process things asynchronously or concurrently, you want to have both metrics, both TPS or throughput and latency. So they are inseparable. And imagine you're submitting a paper to top-notch system conference, and you wouldn't just submit a paper saying, I have 1 million TPS, I have a very high throughput, and they will just reject your paper saying, I have no idea what your latency is, because we can have very high throughput and also high latency at the same time. Mm-hmm. So a good analogy is, a good question is, what's the infrastructure or system that has the highest theoretical throughput in the world? So perhaps people will say, oh, the internet, we are all doing our stuff on the internet. It must have very high, overall throughput. It just moves like terabytes or petabytes of data nowadays. But the answer, it's questionable, because if you only talk about throughput, maybe the logistics, UPS or USPS has the highest throughput. Why? So imagine we want to send something from, like, say, New York to my place, like Mountain View or Palo Alto. It's like coast to coast kind of communication. Mm-hmm. And you would think, okay, the internet must be fast. So if I upload or transfer my files or movies or those large files, I can achieve very high throughput. Assuming I have money, I can get a good ISP. I can have very large bandwidth. Then I don't have to worry about the throughput. But the reality is, the fastest way, or define fastest, the most efficient way to move a large chunk of data is not by the internet or even by network. It's by trucks. So you have trucks packed up with hard drive SSDs or even SD cards, because SD cards may have most of the density, compared to other storage mediums. So media, if you use SD cards and you pack the whole truck with all SD cards, where each SD card is 1 terabyte or 200 gigabytes, whatever, then the whole truck probably is like at petabyte or even exabyte level. So then imagine, although it takes you several days, a couple of days, probably a week, to drive coast to coast from, let's assume it's driving, not by a flight, from New York to Palo Alto, then in that case, if you divide it by the number of seconds you spend throughout all these days, it sounds kind of long. So you assume the TPS would be low, but in fact, the TPS will still be high because of the huge volume of data you are able to pass through along the path. So really, your TPS could be like bizarrely high, could be like 1 terabyte per second or something, or 1 gigabyte per second or something. But that doesn't really help. You definitely don't want to do that, on a daily basis. You don't want to transfer your files using that kind of method. But large companies, I guess like Google, like some data centers, for the data centers, they do want to transmit their data in that way. So they actually have trucks to mail the hard drives because that's more efficient. So because in that case, they don't care about latency. In this case, the latency is days long. It's not about seconds. On the other hand, if you say that, okay, sounds like latency is important, let's only talk about latency, then it's also wrong, because you can easily have a system that has very low latency but very low throughput at the same time. So a good example is you cannot tell whether a bank is more popular or more efficient if you only look at one branch and it looks like nobody's there, or you can immediately walk in and get serviced. You don't have to wait in line, because it's very likely that the bank is not popular. It's so small, so it doesn't have that many customers. It doesn't have much load. So in that case, you are the only customer, so you can just walk in and get served. So latency is nearly zero or very low. So what really matters is, given the load, given the throughput or the capacity of the system. So throughput measures how much data or how much stuff the system is able to process at a time. And plus latency, that's for the user, end user, or clients. This is how responsive or how fast the transactions were processed. These two together can determine the overall performance for distributed systems. And the reason you have to use both is simply because usually these systems have things going on at the same time. So it's hard to tell, because if you assume the system can only process one thing at a time, then throughput is just like the inverse of latency. So then you can see why some projects usually advertise they have very high throughput without talking about their latency. It's because they have to make the trade-off. So in order to have high throughput, their latency must be horrible, unless they have very, very bizarre kind of consensus or their own protocol, or they use sharding. So then
are there any projects that come to mind right now that meet what you're describing?
I didn't want to be offensive, but
I don't want you to take any shots at anybody. I was just wondering, as you were saying that, who's he describing, or who could potentially fall in that bucket? But you don't want to spread any dirt on anybody's name.
Yeah, I don't want to. So you can think about it. So it's more of your judge. If you look at the project and you think about how it makes consensus or how the infrastructure works, it makes no sense if you have bizarrely high throughput and also low latency at the same time. Mm-hmm. And especially when there are many projects advertising, they have like tens of thousands or even a million transactions per second. It makes no sense. Even for Paxos making 1 million transactions, the actual transaction is a tough task in a small data center with 5 nodes. And that took them, decades of work. So you can just think about that as a reference. And then, we can come to the next topic, sharding, because people will say, we can still achieve high throughput. What you're saying is wrong, because we can have, many things going on at the same time, just as you said. Then the question is, the question here is whether you really understand sharding, because sharding is a common technique in database or distributed database. And it's not it's not nothing new, because many people may think, especially if they are not familiar with the modern, IT industry, the cloud computing world, they may think, oh, sharding is something cool and new, but it's not new. And it's not cool. It's just like a regular optimization. Right. So the reason, first of all, of course, like many other concepts like TPS, like DAG, it's marketed. It's like a branded. It's some projects or some KOL want to plant this idea deeply into your mind. So sharding is important. Sharding is the key to solve every problem. But what they didn't say, yes, it does solve some problems. So it's not like, I'm going to tell you sharding is useless or something. Sharding is useful, but sharding also has a lot of restrictions. It's more like a trade-off when you think about sharding and replication. So what is a replication? what blockchain tries to do is actually replication. So instead of having a ledger fully, in custody by some authority or some company, you want to spread out the ledger to the entire network. So in that process, you're creating duplicates or replicas. That whole process is called replication. And the entire consensus thing that I talked about is about achieving consistency across the ledger, across the states during such replication process. So replication gives us fault tolerance, because we know if some nodes fail, the rest of the network still have the state intact. They can still move on. And that's also the reason that this kind of protocol is used for cloud computing, because for cloud computing, we definitely don't want the network to be down simply because one machine is stuck or down. And then replication is good, but we also realize that replication sometimes is not necessary for some tasks. Like, say, for a very realistic scenario, we have like one bank which has two branches in two very different cities. Let's just assume, again, one is in New York City, the other one is, Palo Alto or San Francisco. And very likely, people won't transfer a lot between these two cities. So if you're a local in New York City, perhaps for most of the time, you're just paying for your rent, or you just get direct deposit from your employer within New York or within New York City. So if there's these two places are too isolated, then we realize that perhaps San Francisco branch doesn't have to store the entire database or the user information of the residents in New York. So they don't have to exchange their data fully, because it doesn't help. It's good, it's safe to have an extra copy, but if you assume that one side never fail, or you assume that they seldomly connect to each other, then it's fine. So this basic notion or concept is called sharding. The sharding is a way to spread out data by not by replication, but by cutting it, slicing it up into different parts, and each part is unique. It's not identical, the same part. So with that said, these two things are like the two extremes. So do you want full replication or full sharding? Perhaps full replication is useful, because that's what Bitcoin is doing, and most of the blockchains are doing. Full sharding is not useful, because full sharding is like we just run our own little nodes, no other nodes in our system, because you can call all the nodes, they are in the same system, but if they don't communicate, they don't share or exchange their data, they just proceed with their own logic or own protocol, then it's more like effectively n different systems, and you just call them one single system. So it's more like thought experiment. And what we really would like to achieve is try to find some middle area. So this is why normal distributed databases or the service like Google Spanner uses both. So it both has replication and sharding to achieve the maximum performance. So on that front, yes, sharding does help with the performance, but you cannot shard indefinitely. So in the worst case, the system is not interesting anymore because you don't have interaction. Once you want to have interaction, because I also saw the argument that some people saying, we can still shard, we can have parallel chains, and then finally they communicate with each other and get integrated together by a main chain or by some aggregator. Then we have communication. So what do we actually lose in this case? And the thing here is, if you think more about it, yes, you can have a bridging part. You can have a main chain and parallel sub chains, which is the common idea by many projects. I think including Ethereum 2.0 to try to scale up the whole thing. But of course, you're making some compromise. This is not free lunch. The compromise here is, if you really want to achieve the same level of experience for any cross sub-chain transactions or any transactions to make them all uniform, then that's equivalent to doing a consensus. So then you're getting back to the case, because if you think about it, okay, we have multiple chain, we want them to communicate, we want the data to be consistent, and we want it to be generic. So, performance is identical everywhere. And doesn't this sound like designing a PBFT or a consensus protocol like that? So it's more like, making trade-off. It doesn't mean one way it doesn't make sense. It's more like, depending on your application, you might want to choose some level of sharding. But the current misconception is people just blindly believe sharding is the cure for everything. So that's the second thing. Yeah.
Got it. And third point is?
Yeah, the third point is, as I mentioned, proof of work versus proof of stake. Still, there has already been 5 years since I moved to the US, since I, got into the blockchain area. People still come and ask, Ted, is your protocol proof of stake? Or, how is proof of work compared to proof of stake? And, oh, this protocol is bad because it's proof of stake. It's bad because, it's proof of this, proof of storage, proof of space, proof of space time, many things. So I guess many people are also confused, like, what is proof of something? And I actually wrote about it in my dissertation. You shouldn't blame yourself. You shouldn't feel very ashamed if you don't know about it. I didn't know about it when I first came to the space. I got also confused. And not only me, but many researchers, academic researchers, even professors in the field, they're doing legit research. They still didn't realize, or they still get confused by the notion of proof of something, because people usually assume proof of something is the consensus mechanism. And it may sound like so, because I already mentioned there are two families, proof of work family, the other family is quorum family. You will say, oh, that's the proof of stake family. But the reason that we have, first of all, the correct answer is proof of something is just an admission control. So what is an admission control? In your system, although the algorithm usually assumes, oh, there are end nodes, but there's a way that these end nodes enter the system, right? Because for an open system, you cannot simply just assume, let there be end nodes. There are end nodes. So definitely admission control. Then the question is, when do you admit a node? And because you cannot just let anyone join the system, because for vote-based protocols, their safety is based on the number of identities. Like, as I said, a third of the nodes are Byzantine. It's not like a third of the computational power is adversarial. Whereas for Bitcoin, it's different. It's based on computational power. So it's a bit different story. I'll talk about it in short. So for that, those protocols which do not consume a lot of realistic resources, it's very easy for a hacker to just run like 1,000 nodes. Like, it doesn't hurt, right? As long as I have enough bandwidth, I can just start a bunch of virtual machines, or even just in one machine, I run 1,000 processes, and each one is a node to join the system. There's no entry barrier for the system. So then your system can easily be overwhelmed by random, nodes, and the assumption for a minority adversary is easily broken. So one way to address that is assume, okay, we have a special committee, then you become permission, say, oh, you have to, call me to at least let us know, or we have some more automated process where we make a consensus, vote for whether some nodes should join, and we can control, the rate of nodes joining the system, so our system won't be overthrown by newcomers. And of course, the easiest way is whenever you join, you have to lock up some money. So the reason behind is we're assuming not every people is super rich. And as long as we assume that, the system is good, because in order to launch such an attack, you have to have a lot of money, and you have to lock up that amount of money. So But you think about the other side. You think about that's proof of stake protocol that everyone has heard of. So for proof of protocol, what it tries to do is very similar. So when it comes down, it really comes down to the foundation. Proof of work is a matter of computational power, and the computational power is just is a matter of money. Because if you have more money, you can buy more graphics card or buy more, miners, and it's more or less the same. And the reason that by assuming nobody can have more than 50% of the mining power is also by assuming that person or that entity cannot purchase that much of the computational power. Because assume either like the US or China or any country in Europe has a supercomputer that calculates proof of work is in secret. It can overthrow the system, because that's, the whole government is trying to devote its resources to that purpose. So on that front, they're same as for the fundamental reason. And the reason that why people get confused by these two categories is because of Bitcoin, because Bitcoin is very special. So what it tries to do is, as I imagine, originally what Satoshi tried to do is just want to have a decentralized payment system that can be used for the group. They have like a libertarian or anarchist group, depending on how you believe in their ideology, but they are of course, at least libertarian. So they want to have a system that's not controlled by the government. So they just derive the product or derive the system from the idea. They just design a solution directly. It's not like our regular research process or industrialization process, because usually for Google, for cloud computing is, we want to reach that goal, and now we have some basic building block. Then we just put the basic building block together and keep refining each part until we have the final solution. So we can easily say, oh, this is this layer, network layer, we have consensus layer, we have, like the state machine or virtual machine for Ethereum. So it's layered. But for Bitcoin it's special. It's just like an entire solution. So here it is. So this is the longest chain rule, and it works. And then people realize that, okay, the entire solution solves the problem of BFT probabilistically. So you can also regard it as a consensus protocol. So consensus is part of it. So you have to have that to solve the problem. But the other half is it also naturally has the admission control because of proof of work. So proof of work actually there in Bitcoin indeed plays in two crucial roles. One is for the core consensus mechanism, and the other one is for admission control. But proof of work alone is not a consensus protocol, because if you think about it, what's really consensus in Bitcoin is you have to have a chain, and each block has to contain the hash of a previous block. So that's the blockchain, and then each block has to have a proof of work. So the chained proof of work, the whole idea is the consensus. Proof of work is like a crucial ingredient to the consensus. But at the same time, it also serves as a admission control, which is good. But that doesn't necessarily mean every system has to work that way. So that means, a consensus doesn't have to have a proof of work or have to have a proof of something. And for those pure consensus protocols, which don't have any admission control, because don't forget, Bitcoin is like you have a consensus plus admission control. So for a system that doesn't use proof of work, which can be used as admission control, you have to use something aside the consensus to control the admission. So that's when people talk about proof of stake. So in the end, too long don't read version for this question, for this misconception is proof of something is just admission control, but for Bitcoin it's special. It's also part of the consensus mechanism. Mm-hmm. But for anything else, including Avalanche, including Snowball, including hot stuff, PBFD, anything else that does not use mining, proof of work, they must use some admission control. And this is why you call them proof of stake, because typically they use proof of stake, because they don't rely on proof of work as part of the consensus. Then it makes no sense for them to use less efficient proof of stake to do admission control, because for only control the admission, proof of stake, proof of work, they serve for the same purpose. They are fundamentally identical because both are economic arguments. Or you can assume there's a committee, and then you make the system, half open, or it's like a consortium or permission system. Yeah.
By admission control, is that the same thing as Sybil protection? It seems like you're describing the same mechanism.
Yes. So that's also called Sybil prevention, or Sybil attack prevention. Yeah. So the reason I didn't mention the name Sybil attack is because too many words, too many terms here. Yeah, but it's also known as Sybil attack. People. I don't think a lot of people know about the word Sybil attack. They know about proof of work, proof of stake. Mm-hmm. But the admission control is mainly for that purpose, to make sure the assumption, the safety threshold, the minority of adversary assumption is still held in the system.
Well, thank you so much, Ted. That was just an awesome, deep dive on all of this. And I definitely learned a lot, and it was great learning a bit about your background too. Where can people find you if they want to follow you on Twitter, or where's the best place to keep track of your work?
Oh, my work. I do have a personal website. And it's also, I think I also tweet, not very frequently, but I tweet now and then on Twitter. And you can even see my recent rant about, misconceptions. And I'm active on Twitter. I also have like a Telegram account.
What are your handles?
Good question. I'll give you
I'll
later.
definitely put it in the description below.
Yeah, just put it below. Yeah. And also by email, or I'm pretty reachable. It's not like I don't reply to anyone. It's
you know a lot about consensus. You could learn a little bit about self-promotion.
Yeah, but as a researcher, we usually don't tend to promote ourselves that much. It's a good mental state, if you're not saying, oh, I'm the best, I'm the leader, you should listen to me, then you can be more inclusive. You can hear different ideas, and then you have a more like calm mind and unbiased thinking in the process.
Well, one day you'll have a podcast and you'll understand.
I see. Okay.
So for anybody looking to follow Ted, I'm pretty sure your Twitter handle is at Ted Derminant or something like that. But
it's like that. Yeah.
You can follow me on Twitter.
And many people take it as tendermint. It has nothing to do with tendermint. It's just close though.
I got determined, like determinant.
Yeah, that's right. So determinants is, I think it was registered on Gmail or something. So I had to reverse the first three letters in determinant. So it's like Ted Derminant. That's why I got the email address, and also why I had that handle somewhere. Yeah. Somewhere like on Twitter, probably not on Twitter, but on GitHub, I use determinant. So yeah.
Go for it, Connor. You want to plug yourself?
Yeah. So just if anybody wants to follow me, you can follow me on Twitter at DAS_Connor, DAS_CONNOR.
Yeah. So thanks you guys so much. Thanks for the time, Ted. That was really amazing, man. I'm telling you, like I could listen to you talk forever. You have an open-ended invitation anytime if you ever want to join us again, if you have a project you want to plug, if you just want to chat or anything, honestly, man, you have an open-ended invitation. Just give us a shout out and you're welcome anytime. Connor, obviously, thank you for everything as always. You're a rule and you know it. Myself, I want to just give gratitude to everybody in Wyoming. I was in Wyoming for the WYO Hackathon last weekend, and I got to connect with Caitlin and Tyler, and just something special is going on in Wyoming. I'm hoping to have her on the podcast soon so she can give us a sense of what's going on there. And so just thank you to everybody who made it this far, and we will see you on the next edition of the Subnet Show. And so from Snowflake to Avalanche and through consensus to the stars. Thank you, ladies and gentlemen. Cheers.